I kind of need to make this closer. All right, so thank you for having me and for the opportunity to present my work. It's always a treat to talk about my research work. Question is how I move the next one. Okay, there you go. So I plan my presentation into like two parts. In the first part, I talk about my experience as a graduate student at School of Statistical or Mathematical and Statistical Sciences at Clemson University. In the second part, I'll discuss my research, where I'll start with some motivating examples, then some preliminary information about how to model this phenomenon direction, and then I will be focusing more on my recent work, which is about jointly modeling wind phenomenon direction. There'll be some applications of our work, and then finally I'll wrap it up with a short discussion about my future role. So currently I'm a fifth-year graduate student in the School of Mathematical and Statistical Sciences. I'm a former high school math teacher. If I would have to put my research interest under one hat, I would probably say that I'm interested in mathematical and statistical modeling of environmental phenomena. Currently, I'm working on modeling wind and wind direction using statistical approaches. So everything started in my Stat 80/20 class. It was taught by Dr. Whitney Huang, and he asked us about our research interest. And at that time, I wanted to work with time series data, that is data that is measured over time. And he suggested that I look at some wind speed data, see how I feel about it. Maybe we can collaborate on some project. And that's how he became my advisor. And that's how my work on the wind speed and wind direction came alive. A small portion of the data he gave me is plotted on this graph here. These are wind speed measurements that are measured at one location in Netherlands. And they are measured during the month of July over the course of 10 years. So when you get some data about a variable, let's just say wind speed, you want to first know about the distribution. So in elementary statistics, you learn that you can divide the data into bins, tally your data in each bin, and then get a sense about the frequency. Putting these frequencies together, you get what is called a histogram that is shown on this slide here. Now, if you would take those frequencies and you would divide them by the total number of values you have in your data set, you get probabilities. So now we have probabilities that are computed using your data. So these probabilities depend on your data. So we have a mapping situation about which we can think as a function. And actually, they have a specific name for these type of functions, probability density functions. And there are many probability density functions you can use to represent your data. And each of these probability density functions, they are actually governing a distribution. A common distribution that is well known is the normal distribution. The probability density function of the normal distribution is that bell-shaped looking curve. But there are also other distributions such as Weibull distribution, exponential distribution, and you can learn about these distributions in a statistical inference class. So once you have your distribution or your probability density function, what you want to do is to relate it to your data. This process, what it's called estimating your function, or they also call it fitting the distribution to your data, or some others call it modeling your data. So this estimation actually goes with estimating the parameters. My focus is on these distribution functions that have parameters. For example, just a quick side note, normal distribution has two parameters, the mean and the variance. Weibull distribution has two parameters also, the shape and location. So when we are estimating or relating these probability density functions to our data, we are actually estimating these parameters. And we learn ways to estimate them in these parameters in a general linear hypothesis class. Now, it might be that you can have more than one probability density function that relates to your data. And in that case, you ask yourself which one is the best, or which one fits the data better. And in that case, methods to solve that question are taught in data analysis or regression analysis classes. Now, behind all of these statistical concepts, there's a lot going on. And to understand the process of these statistical concepts, it's important that you step outside of your topic and take some classes from different disciplines, such as matrix analysis, real analysis, measure theory, linear programming. You might need to step outside of your school, attend some workshops to learn some tools that you need for your research, but they are not offered at your school. So that's about the classes and how you start becoming a researcher. You start learning about what is of interest to you. Next, as a young statistician, you want to be known, and you want to learn. And one way to do that is by attending conferences. These conferences, some of the conferences that I attended, I put them on this slide here. The top 3 are topic specific. They are statistical conferences. Joint statistical meeting is very similar to the joint mathematical meeting. I think, yeah, joint mathematical meeting. ENVR workshop specific for environmental variables. But I also attended some local conferences such as Math for All, Satellite Conference, the Palmetto Symposium, Strive for More. And I also listed the last one here, the Institute for Mathematical and Statistical Sciences, just because this organization focuses on or offers conferences for mathematical sciences, not just statistical sciences. So when you go to these conferences, what you want to do is to learn. You want to keep yourself updated to what's happening out there. You also want to meet new people, collaborate, construct your network. But you also want to show your work, showcase your work, your research, and you can do that through poster presentations, contributing talks. And then once you get a little bit more senior, you can also do some invited talks too. Now, to attend these conferences, however, you need to pay for your lodging and travels, and that's where travel awards come in. You can apply for different travel awards. The ones that I applied for were in conference participation awards. Some conferences offer awards if you are presenting in that conference. I also used the Graduate Student Travel Award, and I also had the department to sponsor some of my travels. And then finally, another good thing to attend conferences because you get a chance to win awards, and you can put them on your CV and become a better candidate for the position you want to have. Now, talking about the awards, I also want to mention some fellowship opportunities. There are 3 that I know of, and then these are the ones that I had experience with. The first one is Tommy Doctor Dissertation Completion Fellowship. This is for students from underrepresented diverse background who want to pursue a PhD in a STEM field. The other one is the Clemson University Doctoral Dissertation Completion Grant. This is for everybody. These 2 are for your last year as a graduate student. And then there's also Dr. Kenyon Perry Graduate Fellowship. Now, I applied for the top 2. I received the first one, but I didn't receive the second one. And then the third fellowship came as a bonus from Dr. Lopez. And then this week, I attended a Grad 360 event where I learned that Clemson has other opportunities for fellowships, and you can find them under the Office of Major Fellowships. Now, I believe it would be unfair if I would be talking about my experience without mentioning some challenges that I had while I am a graduate student. One big challenge was that sometimes the requirements, they felt like they were overwhelming. Like you have 3 courses to take, you also have to teach or grade, and then you also have to get ready for your preliminary exams. So it worked for me is when I felt like overwhelmed, just took a walk or took some mental vacations or went for a hike or so. But I think the biggest one was this feeling that I don't belong in graduate school, and I learned later that that's called the imposter syndrome. And the medicine for that was I got it when I attended this plenary talk where some professors from different universities came and talked about the experience from going from graduate school to assistant professor. And there was this professor who mentioned that one feeling that most of these students have, it's the imposter syndrome. And she said that she, as a senior professor, sometimes feel that she doesn't belong in her field or in her school. So when I heard that others also go through that, more senior researchers with more experience, professors also have this feeling, maybe feel a bit better. And then the last one is something that I recently experienced when you sit down and you need to write about your research and nothing comes to you and you just stare at your computer. And I learned this way that it's called blank page syndrome. And they suggested that what you can do is just start beginning writing or write your thoughts. I have to discuss this method here. This method is about modeling wind speed. I need to go and find some references about it. Just write this down. And then you can always go back and revise your writing. It doesn't have to be perfect from the beginning. So this kind of wraps up the experience I had as a graduate student. If you have some questions about it, I can answer them now, or we can just leave them for the end of the talk and we can come back and visit them. All right, so now to the fun part. So as I said, I research modeling wind speed and wind direction. But before I get into my research, I would like to take a moment to define what wind is and talk a little bit about how ways we can represent the wind vector. So as we can see in the left picture, wind is an atmospheric circular motion that arises when warm air is replaced by cooler air, for example, or cooler air is replaced by warm air. There are two ways we can represent the wind vector. One way is what is called through the Cartesian coordinates. They are labeled by UV on this slide. They are also called the zonal and meridional velocities. The other way, the second way to represent the wind vector is to wind speed and wind direction, which is labeled by R and phi on this slide. So should you have the data given to you in one form, you can always transform it in the other form using the transformation formulas on this slide. Now, my focus is on modeling wind speed and wind direction. So we're going to box the UV representation for a different time, and we are going to focus only on modeling wind speed and wind direction. So near surface wind speed and wind direction play an important role in numerous fields. I said near surface because what I'm looking at is at wind speed that it's measured 10 meters or 20 meters above ground. So fields that use wind speed and wind direction are, for example, pollution modeling, where computer experiments that are used to model the behavior of the pollutants in the air use wind speed and wind direction as inputs. In building engineering, builders can use wind speed, for example, to get a sense about the strength of the material they need to use. Also, architects who want to design climate-friendly houses, they must consider wind direction that can be channeled to the interior of the building. In clean energy, wind speed and wind direction are significant in designing the layout of the wind farm in such a way that the power the wind farm puts out is optimal. Power of a wind farm is actually a function of wind speed Q. So that's why it's important to consider wind speed. So having such a wide range of applications, it's important that we construct methods to accurately model wind speed and wind direction. So on that note, there are, I don't know how to make this going. So there are many distributions that are proposed in the literature for the modeling of wind speed. However, the most commonly used one is the two-parameter Weibull distribution. This distribution has the probability density function given by the equation in this slide, but the equation is not that important. The important part is the fact that this distribution has two parameters, alpha shape and beta the scale parameters. So to show you that the Weibull distribution is indeed a good distribution to represent wind speed data, I'm using the same wind speed data from the previous slide, and I fitted three different distributions. The red curve here represents the Weibull distribution, the orange curve represents the gamma distribution, and the purple curve represents the inverse gamma. So to see which of these three distributions approximates our data well, we construct what is called a quantile to quantile plot, or QQ plot. Now this QQ plot is actually a scatter plot, where on the x-axis we have the empirical quantiles, and on the y-axis we have the model-based quantiles. Now empirical quantiles are quantiles of your data. Model-based quantiles are quantiles from your distribution. Right? So we have quantiles from the Weibull distribution, from the gamma distribution, and from the inverse gamma. So what we want to see here is for these points to line up in a straight line. And we see that that happens for the Weibull and gamma distribution. However, the Weibull distribution is closer to our line at the end as compared to the gamma distribution. This means that the Weibull distribution does a better job of capturing the tail behavior of the wind speed distribution. All right, so I need to go to the next slide. There you go. So that was wind speed. Now about modeling wind direction. Before we get into the modeling part, we have to point out one important fact, and that is that wind direction is a circular variable, meaning that values with modulo 2 pi are the same. So if we would want to represent wind direction data through a histogram, as shown in the first figure here, we would probably omit the fact that the 0-degree angle and the 360-degree angle are the same. This property is better captured by the circular histogram shown in the white diagram on this slide. So when we look for distributions for modeling wind direction, we need to focus for a specific part of statistic called circular statistic. One such distribution from the circular statistic is the von Mises distribution. Again, this is the equation given for the probability density function, but our interest is on the parameters kappa and mu. We have again two parameters here, where kappa is the concentration and mu is the wind direction. Another part that I would want to point out is that a component of this distribution is the cosine function, and we know that cosine function is a periodic function, so it's good to capture the periodic property of wind direction. So it is often the case that we have a multimodal wind direction data. This happens, for example, when we are looking, we have data, wind direction data that is measured every, say, 10 minutes over the course of 1 month. So in that case, we can have direction that is prevailing during nighttime and another different direction that is prevailing during daytime. Also, we can have a situation where our wind direction data is measured every day, once a day, over the course of 1 year. So in that case, we may have prevailing directions for summer season, which are different than prevailing directions during the winter season. So in that case, we have what is called the multimodal wind direction data. And the models or distributions to model such data, one distribution can be the von Mises mixture distribution. Another one that is often used is what is called the normal mixture distribution. Now, we call a mixture a mixture distribution when we put two or more distributions together. So von Mises mixture distribution means that we put two or more von Mises distributions together. And to show you again about fitting a multimodal wind direction data with a mixture distribution, we plotted some wind direction data that is measured at the same location as the wind speed previously shown, but this data is actually during the month of January. So we fitted this data with two distributions, a two-component Von-Mises distribution, which is labeled by the red curve, and the two-component normal distribution, which is labeled by the black curve. So from the quantile to quantile of QQ plot, we see that in this case, both distributions do a good job approximating our data. So I got a little bit technical and I'm ready to get into the joint modeling, but before that, let me just pause for a second, see if you have any questions. Okay, so now that we know, we have a brief idea how to model wind speed, how to model wind direction. We are ready to put that together and talk about my recent work, which is jointly done with my advisor, Dr. Whitney Kwan, and some scientists from the Oregon laboratory. So what we want here is to construct a method that allows us to model wind speed and wind direction measured at one location during one season. And the way we approach is to decompose this joint distribution. When we put two variables together, we have a joint distribution, by the way. So the way we approach it is to decompose this joint distribution into the product of the marginal distribution of wind direction and the corresponding conditional distribution of wind speed given wind direction. Now this decomposition, I think it's taught in an early probability class, like 8,000 or so in this at this point. So then once we decompose it, we need a distribution for each of the components. For the modeling of wind direction, we just learned that we can use a Von-Mises mixture distribution. So this leaves us with the need to construct a distribution that we can use to estimate the distribution of wind speed given wind direction. We're going to call that the directional wind speed distribution. So the way we can approach the construction here is to use a distribution that is commonly used for modeling wind speed, such as the Weibull distribution, in such a way that the parameters of the Weibull distribution are functions of wind direction. So since wind direction is periodic, right, those functions, they need to be able to capture this periodicity. Such functions are periodic functions, like sine and cosine functions, for example. So once we have this dependence of the parameters of wind direction constructed, we know the distribution of our wind speed, and then we can characterize it or represent it through quantile curves. Now, a short parenthesis here, when you do regression, usually regression is done on the mean, like we are approximating the mean of our data. However, we can also approximate the median, or we can also approximate the 75th quantile or the 95th quantile. And that's the approach we take in our work. So here, the blue curve represents the median of our proposed distribution. The black curve represents the 75th quantile of our proposed distribution, and the red curve, the 95th quantile. And we also plotted as points the empirical estimates of the quantiles of our data. So these are the points represent the quantiles of our data. And we see that our quantile curves are very close to these empirical estimates, meaning that our method or our distribution approximates those empirical quantiles very well. So the core of our work is the construction of this directional wind speed distribution. So I would like to take a few slides to explain the process we follow to construct this distribution. So again, we start with wind speed and wind direction data that is measured at one location during one season. We divide the wind direction data into n beats. In this example, I'm using 9 beats. This is what is called binning the data. So we have 9 beans, and then in each bean, they're going to fit a Weibull distribution to the wind speed. And from each fitting, we get estimates of the parameters. And we also represent the wind direction in each beam by the direction median. So in this stage, we reduce the wind speed and wind direction data to the parameter estimates of each of these variable distribution and direction medians for each of these beams. So this gives us a new set of data that we can use to construct the dependence of the parameters through on wind direction. And if you remember, that dependence is constructed using a periodic function. In this case, we actually use pairs of sine and cosine. Some of them, some call them Fourier series. Statistically, this part here is called harmonic regression. So we are regressing the parameter estimates on wind direction using harmonic functions. And the outcome of our regression is the black line on this graph, and then the points, they represent the parameter estimates from the previous step. And again, we see that these curves are very close to our points, meaning that they estimate them very well. So this gives us, again, the dependence of the parameters on wind direction, which means that we know the distribution of the directional wind speed. So to just sum the methodology up, we started with wind speed and wind direction, right, measured at one location in one season, and we took the joint distribution and we split it into the marginal distribution of wind direction and the directional wind speed distribution. For the marginal distribution of wind direction, we use a one-basis mixture distribution to estimate it. And for the directional wind speed distribution, we use a two-stage approach, where in the first stage, we beam the direction data from each beam, we calculate or estimate the wind speed data, and we reduce or represent wind direction by one value. And we use that data from stage one in our harmonic regression to get the distribution. So we call our directional wind speed distribution, or the methodology, the beam variable harmonic regression, and we use the BWHR acronym to represent it. So now that we have a model, we can use it in some applications. So what we are interested in is to estimate how the joint distribution of wind speed and wind direction changes from historical to future climate scenarios. Now, climate scenarios are with respect to carbon dioxide levels. There are different climate scenarios out there. One that we are using is called business as usual. This means that there's nothing done to reduce carbon dioxide. So we continue to do whatever we've been doing. So that's the scenario we are looking at. There's also other scenarios where you are reducing the carbon dioxide by different percentages. But again, we look where the carbon dioxide is not reduced. It's called business as usual. Now, another fact is that it is well known in the literature as this carbon dioxide level grow, other environmental variables such as temperature or precipitation also increase. However, there is not much information about wind speed and wind direction, or there is not clear, let me say, put it that way, there is no clear information about the distribution of wind speed and wind direction. Some would even go and say that wind speed and wind direction doesn't change from historical to future climate scenarios. So what we want to do is to see if our method can help us, add to these findings. Since we need to look in the future, we cannot use observations. So what we have to do is to rely on what is called climate model output. So the way I like to think about is climate models, there are a bunch of equations. Most of them are partial differential equation. Each equation represents some kind of scenario of the atmosphere. And then we put them together and you solve them and you get an output. And a portion of that output is wind speed and wind direction. And the model we are looking is actually has a 3 hourly wind speed and wind direction measured every 3 hours, and then has a resolution of 12 kilometers. Now, this means that observations, for example, are point-wise. Like we have a station here, and then we measure wind speed and wind direction at this station. So that's a point. Climate models, they work a bit differently. they work, some of them work in a square, and I think this one works in a square. And that means that if we would be in the middle, we will have to go 6 kilometers north, 6 kilometers south, and then 6 kilometers to east and west. And that's how we get the square that wind speed and wind direction represents. But anyway, so we do have our wind speed data now.
I have a question.
Yes,
So you said the historical 95 to 2004.
yes.
How do you have any idea how far back the data goes that's usable for you? I mean, does it go back before 95?
So this particularly, I'm not sure, but I know there's a lot of work done to. There's a name for it, but I can't remember. So instead of forecasting in the future, they backcast.
Oh.
So they go all the way back to. Yes.
Yeah, because I mean, my question is inspired by, you know, it occurs to me that you're looking at things that they might not have even considered in the 1940s or something like that.
Yes, and there is work, some statisticians actually work on that, and I just learned that last semester.
I can tell you, from trying to do research, just to support a historical novel, make it accurate, the data gets thin really fast. Remember, there were not global weather observations until 1945, and that's just at middle latitudes. And most records you get, I downloaded like it's 2 gigabyte index of data around the world, is only daily observation.
Yeah. Okay, so we have the data. We are not going to look at everybody. We're just going to look at 3 different locations. We're going to we chose Texas, North Dakota, and some mountain area of North Carolina. And the way we chose this location is with respect to wind direction. So we look only at summer season, and what we wanted is for a wind direction to be concentrated around one direction only. And then another direction that has a more like a uniform distribution, and then a third one, distribution between these two. So to look for changes in our wind data, we start with looking for changes in the wind direction data. To do that, we fit a von Mises mixture distribution to the historical and future wind direction data for each of the 3 locations, and we plot the estimates on this slide here. The red color is the historical estimate, and the blue color is the future estimate. And we see that at 2 of these 3 locations, there is not a significant difference in the wind speed direction, since these distributions almost overlap each other. Middle location, there is a little bit. So our findings still align with the findings in the literature. Then we go to see if we can identify any changes in the directional wind speed distribution. So to do so, we take the historical and future data, and we fit it using our mean variable harmonic regression method, and we compute the quantiles. Now we have future quantiles, and we have historical quantiles, and to see for changes, we look for, we subtract them, we look at the differences. So what I have plotted here is the difference in the future and the historical 95th quantile. And these differences are represented by the solid curves on this slides. We also look at the changes in the wind speed distribution. Right, so we compute the differences in the future and historical wind speed distributions, and we plot these differences using the horizontal dotted line. And I would like to just point out the third location, North Carolina mountain area, where the horizontal dotted line here is very close to 0, suggesting that there is not a significant distribution in the wind, not a significant change in the wind speed distribution. However, our method was able to identify some significant difference in the variation of wind speed with respect to some of the wind directions. So we feel that these findings can be of benefit for some of the applications of wind speed and wind direction data. So to summarize our method and my research work, we started with wind speed and wind direction data, and then our method decomposed this joint distribution into the model distribution of wind direction and the directional wind speed distribution. And then we needed a model for the wind, to model wind direction and a distribution to model or estimate the direction of wind speed distribution. And we used the literature for wind direction to get the wind speed spatial distribution, and we constructed the wind variable harmonic regression method to estimate the direction of wind speed distribution. Now, to just remind you, this work is done for wind speed and wind direction that is measured at one location in one season. Most applications work on like wider area than just one location and multiple locations. And also they look at, not just one season, but multiple seasons. So that's where you get some spatial and temporal modeling. If you look at more than one location together, like I have here plotted in the very left picture, wind speed, half of over the half of the United States, and we see that in wind speeds over water are higher than wind speeds over land. Furthermore, wind speeds that are close to each other are similar than the wind speeds that are further away from each other. So we see what is called spatial coherence, spatial dependence. So we have to account for that in modeling spatially. In the case of temporal modeling, right, we see that wind speeds in the winter seasons are higher than wind speeds in the summer seasons. So again, we have to account for this temporal dependence in our data. And that's what my work is, or I'm working on right now. And just to give you a big idea, is the way we usually approach this space-time modeling or spatial temporal modeling is to look at the global structure and local structure. And then the global structure is also called the trend. And then the local structure is what we refer to as residual. So when you model the trend, you use covariates. In our case, the wind speed location, it's one of the covariates that we use. In case of the temporal for trend, we use periodicity. Like we tend to see the same type of wind speed like every January. Like if I look over the course of 3 years, each year we'll have about the same type of wind speed in the month of January. So yeah, that's a periodicity model. Then you are left with the residuals, and that's where it's complicated. Residuals, in modeling the residuals, when you want to account for this spatial coherence I was talking about not too long ago. Right? Look at or account for locations that are close to each other, and opposed to locations that are far away from each other, and so forth. So that's what I'm working on right now. Hopefully I'll get it done by August, and then I can finish it. But yeah, that's my research work along with my experience at Clemson. And if you have any questions, I'll take them now.
Questions? One I have about to talk, the Weibull distribution. It was like a couple of parameters. One of them was alpha that was called shape.
Yes.
So that's a numerical parameter, like a positive real number or something like that.
Both of these parameters, yes, are positive.
So
yes.
Can you describe how shape is parameterized, or maybe that's just a word that you use, because when I think shape, I think of shape. So
okay, so I think if the best way to relate to like normal distribution, you have the mean there, and then you have the variance or standard deviation, and the mean kind of tells you, since the normal distribution is symmetric, the mean tells you about the middle part and the peak of your bell shape and all that, and then the variance tells you how your data is spread from the mean.
Okay.
Like how far.
So this is
So that's how shape and scale.
That's what it means by shape. Is how the bell curve's kind of.
That's right. That's right. Yeah.
Okay. Thank you.
Yeah.
While that plot is up, I got a comment on the fit plot. I think it's always worth mentioning that fit at the extremes, even though looking at much fewer events, are much more important. That's what Roswell looks at.
Yeah, so, my advisor, Dr. Pine, he's an extreme value analysis expert. I didn't get a chance to go into that, but you are right, yes. So when we get into, the modeling of the tail of our data, we don't use, values, which are right here. Joyce is also an expert in extreme value, so she can tell you more about it, but yeah, you have to change your modeling into and use distribution from the extreme value theory.
I've been looking at a lot of financial data lately. and
Okay, yes.
people For many years have not allowed for the extremes, and those people are broke.
Yeah,
Yeah, for extremes, is one thing we need to notice is that that's the limited distribution, so it depends on like how big the sample size gonna be. So if the repeatance is not big enough, it's hard to say this is close to the extreme values. That's the one part that's to be aware of.
When you think about financial data, you have all of the things in common. Price was this on this day, it was this on the next
yeah.
day, no debate.
When you look at these vectors, each point is like a position and velocity, or not, direction and velocity, right?
So my points are direction and the speed, yeah. So, where do I have some points?
So
Yeah, so we go direction, so we have this north direction, all the wind speeds here, like for that north direction, then we have this northeast and all the wind speeds for that.
yeah, so that's like your vector field in your, that's like the compilation of your vector field on one chart, right?
Yes,
So when you have your space that you're working in, are you working in 2D space? Like you're treating the surface of the earth as like flat, or are you going like elevation as well?
and so,
Or
yeah, so. Elevation as in like elevation,
elevation would be altitude is this?
Okay, so, yeah, in environmental, the altitude, you know, when we are like sea level or above sea level, that's what you mean altitude, or it is more like theoretical.
I know that they're both two different things. I'm just wondering if you
Yeah.
do like, when you're looking at these, do you separate into that third dimension as well? Or, and if you do you separate into like ground height from the ground, or altitude, like height from sea level?
Okay, I think I understand it, so, it's not like, so all these wind speeds, or the wind speeds that we get, or data that we get, it's measured at one, height. So it's 10 meters, and everything, all the data is 10 meters, it just doesn't happen that today we have 10 meters, tomorrow we have, 15 meters or so. So everything is measured at 10 meters, so, yeah, and then, the way you approach, one way to approach modeling a bivariate vector, because that's what we have here, like the two component vector, is to look for the behavior of the two variables, right, and then the dependence between the two variables. The way we approach it simplifies that. We still, you know, look for the distribution of our variables, wind direction, wind speed, and our dependence between wind speed and wind direction is actually captured in the modeling of wind speed. So we don't really have a third dimension or
Like the position doesn't, you're not worried about the position, you're more thinking of speed and direction. It's the two things that are correlated.
yes. So
Position doesn't matter.
yeah, I think yes, so that's what we do, yeah. So we have the two variables and their correlation, that's all we care for in this case. Now, we do have longitude and latitudes when we get into space-time modeling or spatial modeling, and they can become covariates, like where we are measuring the wind speed, it becomes important. Yeah, so in that case, location can be thought as a covariate, not like it's not part of your vector, still a two-dimensional vector, yes, still a wind speed and wind direction.
I know if you're looking at like the payback of a wind turbine, the government will give you lots of very pretty charts with average wind speeds at different heights of ground.
Yeah,
But it occurs to me that that's largely probably not based on data. They have just extrapolating on some model.
so, yeah, so, you can. Yeah, so you can have wind speed measured at one level, let's say 10 meters, and then you can, transform it to 20 meters, or you can transform it down to 2 meters. And that's what the computer models actually do. They just measure it at one level and then they use some transformation to do it. Yeah, so that is a transformation that you can go from this one level to the next up and down. And there's also some interest in modeling wind speed vertically. We model it, horizontally, but there's also, some interest in modeling, called vertical modeling of wind speed.
Well, I have to ask also, I think you mentioned that you were a teacher.
Yeah, I'm a former high school.
Yeah, so what inspired you to, do the,
To become a high school teacher, or become to the.
well, both, I
Yeah,
guess.
well, I always like to explain math to people, and so that was the option of becoming a teacher. But I always felt like I once I start, studying for my bachelor's degree and learning more about math, I found it, interesting to see how we can use math to model everyday phenomena, and so I went into teaching. I kind of got stuck into it for a while, and but I always wanted to pursue my PhD, and at some point I just had to pull the plug and say, okay, I'm going to do it this time. So, but and then I came to, and then, that's another probably important fact to say, that I came to the graduate school wanting to do work with partial differential equations. In my master's, I looked at modeling the fluid flow, but then if statistics kind of start becoming alive, and more people talk about statistics, and I thought that I might have some better opportunities becoming a statistician. But looking back now, both fields need experts about the same, the same amount of experts you need in both fields. So I think I would have done okay being there too. So yeah, it's okay. I guess I say that it's okay if you change your mind. It's just like you have to catch up what you lost during the process. And then I had something else done. Yeah. Oh yeah, that's what I wanted to, focus more on teaching, but when I started to do research, I liked that, and I started learning about climate change and how how the spread of all kind of viruses and all that can be modeled, and that became more interested than teaching. But yeah, I'll have to do both of them actually. I know I'm still 40 seconds. I'll just say that.
Other
But, yeah.
questions? Okay, let's speak again. Were there any questions out in Etherland? All right. Well, thank you all for showing. Next week, I believe, actually, the AWM is going to have a speaker about Women's History Month, actually. So women in mathematics, that should be a really good one. So mark your calendars for that. Y'all have a good weekend.